simulators are there. As sir is having expertise in those simulators, so definitely attending this session, this particular session will be very much fruitful to for all of us, not even for participant, even for us also it will be very much useful if in future we plan to go for this one. So I will with this I will just request sir to continue with the session. Okay, sir, over to you, sir.
Thank you. Thank you. Thank you so much. Is my screen is visible? PowerPoint slide.
Yes, sir, your screen is visible.
Thank you. Thank you.
Yes, sir, it is video.
Okay. So I welcome you all for QT-03 Basics of Quantum Programming series. And today's lecture, we're going to cover about quantum simulator. Okay. So let me introduce myself officially. I am Dr. Jaykumar Vaidishankar, founder, CEO of Anatandra Private Limited. I am serving as IBM Quantum Educator as well as IBM Qiskit Advocate Mentor. I'm completed IBM Certified Associate Developer Quantum Computing using Qiskit. As mentioned, today's topic is somewhat very much important. If you want to learn quantum, the next step is to do practice in quantum. So to practice with quantum, there are so many tools, so many simulators available. Among all, IBM Quantum Qiskit, which ranks first. So in terms of open access, in terms of flexibility, in terms of features, so IBM Qiskit stand first. So let me introduce what is the meaning of Qiskit. IBM Quantum Qiskit, where Qiskit stands for Quantum Information Science Toolkit. So this is the abbreviation of Qiskit. I will share this link with you. I hope all of you have a Qiskit login. Please go to this website, IBM Quantum Platform. Are you able to log in into this dashboard? Am I audible? Are you able to follow? Great. So please log in into your IBM Quantum account. We already covered how to create an account. If you don't have, please create. So if you scroll down, you can see IBM Quantum Composer. So click IBM Quantum Composer. So all of you click file, select new option. It will land up to this page. So here you can see so many options. Okay, we can do simulation in multiple ways, either by graphical user interface or by coding, Python coding. Okay, so you can do quantum simulation using two options, using composer, GUI based. Next you can do using Python code. So this one is graphical based. Okay, so left side you can see the combination of gates. So here you can see gate collection. So here you can see quantum gate collection, or you can say classical gate collection, gates collection. There are two ways to use it. You can list it out, or you can see in gallery mode. So you can list it out if you click this. So Hadamard is quantum gate. Classical gate, you can see CNOT, Toffoli, swap, identity gate. So phase gate, these are T, S, Z, TG, SDG, phase RZ, all are quantum gates. Okay, if you scroll down, you can see non-unitary and modifiers. So this is not related to quantum, it is related to both classical and quantum. Right? Measurement is not a quantum gate, but it will convert your quantum result into classical version, binary version. So category wise you can see. So these are all quantum gates, pure quantum gates. So visualization also you are able to see over here, right? So if you click this button, you can minimize and maximize these gate operations. So click gallery mode. So I recommend each and every one of you try to switch between the list and the gallery. Okay, so this side is your composer, Qiskit composer. So this is Qiskit composer, exactly equivalent to musical composer. So this side you can notice it is called phase disk. So you can here you can easily get quick output. So these are all called phase disk. Where you can see quick output. Okay. So if you look downside, you can see Q sphere. So Q sphere stands for quantum sphere. So Q sphere stands for quantum sphere. And I hope every one of you know Bloch sphere. Every one of you know Bloch sphere. So both tools used to visualize quantum bits. Both tools used to visualize qubit. But what is the difference? Using Bloch sphere, you can use only one qubit. Okay. Where in case of Q sphere, you can visualize multiple qubit. So this is the basic difference between Q sphere and Bloch sphere. Okay. So in IBM Qiskit, you are able to see Q sphere. Means you can see multiple states of multiple qubits at the same time. For smaller number, it is easy to visualize. For bigger numbers, no need to see Q sphere because it will get confused. You will get confused. Okay. So you can drag and drop. You can resize your window in such a way according to number of qubits. Okay. So what we do, we try to delete qubits. We try to keep only one quantum bit. So what we do, click Q0, select bin button. Click Q0, select bin button. Click Q0, select bin button. So keep only one quantum bit. Do same thing for C4. C4 stands for classical bit. So 4 classical bits are there. So click here, press minus button. Click here, plus minus. Click here, plus minus. Keep only one quantum bit. Only one qubit, which is called Q0. Okay. Keep only one classical bit. C1. All of you able to do this? Q0 and C1. It is a Bloch sphere, but ultimately it will represent Q sphere also. Yes. So downside you can see each and every qubit in IBM Qiskit by default assigned to stage 0. So this is by default. Okay. What it means, we are preparing qubit. We are preparing qubit in stage 0 by default. So it means whenever if you are creating any qubit in IBM Qiskit, it is automatically assigned to stage 0. So in reality, all qubits are in superposition, random position. We don't know what position it going to be. So for that, for all computation purpose, we need to declare qubit in either stage 0 or state 1, because we are able to calculate from known position to known position, or you can say state. If you are doing computation, then it will go for known position or state. So this is why we need to prepare qubit. This is why we need to prepare qubit either in stage 0 or state 1. So this is mandatory. So almost all qubits are in random position. You cannot take a random position qubit. You cannot do computation because you don't know where it will go. So each and everything you need to predict. Okay, at least in your computation. So before creating any randomness in your qubit, it should be in known position. Great. Okay. So initially all qubits are pointed to stage 0. So stage 0 is pointed to North Pole. So this is Northern Hemisphere. Northern, yes, initialization. Great. Northern Hemisphere. This is Southern Hemisphere. Southern Hemisphere. I will tell how to reverse the CNOT. So the whole Northern Hemisphere will represent stage 0. The whole Southern Hemisphere will represent to state 1. But exactly where it will point in North Pole. North Pole. Exactly where stage 0 will point in South Pole. So this North Pole and South Pole are called pure states. So this North Pole and South Pole are called pure states. So stage 0 exactly will located in the entire exact North Pole. Okay, the state 1 exactly will point in South Pole. So because stage 0, your circuit is initialized to stage 0, now it is pointing to North Pole. Okay, so here you can see state vector. So whatever, if you want to represent in graphical, if you want to know its signal strength, you need to look at state vector. Okay, so here you can see computational basis. So one qubit have two possibilities. Either it will have in stage 0 or state 1. That is why we have two possibilities. Okay, now it is pointing to North Pole. That is why the full signal strength is given for 0. So here you need to measure the signal strength in terms of amplitude. So place your mouse over here. Place your mouse over here. Now you can see stage 0, amplitude equal to 1. It means full signal strength for stage 0. So if you're looking at probability, so again you will have two possibilities, either stage 0 or state 1. Okay. Now it will pointing to state 0. So there is a software glitch. It is not showing. Okay. That is why. So move your mouse pointer over your phase disk. You can see quick output. So phase equal to 0, real particle to 0, imaginary particle to 0. Probability of state 1 is 0% because the initial state is stage 0. All of you able to follow? Shall we proceed? Yes, great. We need to use NOT gate to initialize in state 1. So drag and drop the second gate, which is called NOT gate. So this is NOT gate, which is equivalent in classical terms. It is a classical gate. So what NOT gate will do? It will do negotiation. So it will do bit flip. So it will convert 0 into 1, 1 into 0. Okay. So what is the symbol you are using in quantum? So X stands for NOT operation, which is called Pauli X gate. Okay. So NOT gate stands for X. So X state 0, it will turn into state 1. Again apply X. to state 1, it will convert into state 0. Okay. So what happened here? You can observe state 0. Okay, not get applied. The state is converted into state 1. So imagine it is like a switch. Imagine it is like a switch. Associate state 0 in off state, state 1 in on state. So what it means, power supply will happen over here. So power supply will happen over here. So move your mouse over here. You can see the difference. Phase equal to 0, real particles is 0, imaginary particle to 0. But look at the next line, probability of state 1 is 100%. Now if you are measuring this qubit, it will give the binary value 1. What is the probability with 100%? And look at the changes. Initially it is pointing to state 0. After applying NOT gate, so it is converted into state 1. It means bit flip, state flip. Total opposite. Exactly opposite to the previous state. So look at the amplitude. Now it is pointing to 1. 1 contains full signal strength. Amplitude is 1. Now look at the probability. If you are doing measurement, what is the binary value will get? 1. And what is the probability? 100%. Yes, you can ask question. You can put in chat box. Lata Go Hill. Any doubts? Any question until this? Bit flip in terms of classical, state flip. Yes, both are same. That is why I told try to remove all your qubits. Keep only one quantum bit, keep only one classical bit. So click here, press delete button until you attain only Q0. Meghdut Chakrabarti, are you able to delete all qubits? Keep only Q0, C1. So please follow instruction step by step, one by one. Yes, thank you, thank you. So if you want to see the Python code, where you can see, go to view, go to panels, go to code editor, you can see Python code. So this is the equivalent Python code for this graphical circuit. Yes, we can create wait little bit. I'll tell. So visualization seed means how many times you are able to run this circuit. So this circuit is executed 4,677 times. Code, no need to send the link. Go to view, go to panel, go to code editor. Enable this. Enable this. You will get equivalent code. So check in your login, you are able to get the code. Great. So what we have one quantum bit, that is why quantum register 1, comma Q. So 1 stands for number of qubit, Q stands for label. Okay. So here you need to select Qiskit. So two versions are there, Open Quasim and Qiskit. So all of you select Qiskit. So this is your Python code. So don't get confused. Are you able to follow? So select Qiskit option in your code and you can see this code. So line number 5, what we are doing, we are creating classical register. Maybe I can zoom for your convenience. So line number 5, we are creating classical register, which is nothing but C1, right? So 1 comma C. We cannot edit, wait a minute, 1 comma C. So 1 stands for number of classical bit, C stands for classical bit. Okay. So line number 6 is nothing but it is a function call. So quantum circuit Q register underscore Q, C register underscore C. It means it will create quantum circuit 1 comma 1. So 1 stands for quantum register. The next one stands for classical register. So line number 8, what it will do, it will attach your NOT gate. So X stands for NOT gate. And where it will attach, it will attach in Q0 quantum register. So this is the meaning of line number 8. So what we are doing, we are adding NOT gate in Q0. And what is the whole circuit name? The whole circuit name is circuit. So in some cases, they will create circuit QC equal to quantum circuit. So most of the time they will write like this, quantum circuit, right? 1 comma 1. So this will be equal to this one. So you can write in multiple ways. So what is the beauty of this graphical based? Automatically your coding will get changed. Suppose if you drag and drop one more NOT gate, the coding is added. Look at the line number 9, one more NOT gate is added. And look at your output. Look at your output. Stage 0, NOT gate. It means it will do bit flip. State 1, power supply will be there. Again, if you are applying NOT gate, again it will converted into stage 0. So 2 NOT gate will cancel each other, which will go back to original state. Original state. Are you able to follow? Next, what we do, we try to delete this gate. We try to delete this gate and automatically can observe changes in your code. So circuit is empty. That is why there is no more gates. Only until circuit code will be available. I'll go to view. I'll go to panel. I will disable code editor. I'll disable code editor. So we covered 2 examples, empty circuit with NOT gate with one more NOT gate. Okay. Next, what we do? We try to do Hadamard gate. Drag and drop Hadamard gate. Drag and drop Hadamard gate. And what it will do, it will create equal superposition. It will create equal superposition. So what it means, it will generate state 0 sometimes. It will generate state 1 sometimes. So there are 2 possibilities of this Hadamard gate. So that is why you can see output over here, real particle to 1, imaginary particle to 0, probability of 1, state 1 is 50%. Remaining 50% is relevant to probability of stage 0. That is what is half. So half of the circle you can see in blue color, half of the circle you can see in gray color. So this phenomena is called superposition. At the time, pole on south pole, which is nothing but equal superposition. Now look at your state vector, look at your amplitude. Amplitude is divided for both 0 and 1 equally. So what is the amplitude? 0.707. What is the amplitude of 0? 0.707. So literally the value is equivalent to 1 over root 2. 1 over root 2. So what do you need to do to get probability out of your state vector, out of your amplitude? You need to take modulus, then you need to do square. Okay, so do this. 1 over root 2, you are taking modulus, you are doing square, you will get 0.5. Then 0.5. This is what the probability of 0, 50%. This is what the probability of 1, 50%. Are you able to get probability out of the state vector, out of the amplitude? Now is it clear? Why it is 0.707 over here? Why it is 0.5? Great. So what we do? We try to do measurement. Okay. So resize your window. Select this measurement gate. So it will look like a gauge. It will look like a gauge. If you drag and drop, this is Hadamard. This is Hadamard. So Hadamard will create equal superposition. Equal superposition. Okay. So this is called measurement gate. This is called measurement gate. If you do measurement over your qubit, if you do measurement over quantum bit, it will collapse. Superposition and leads to one of the possible states. So listen carefully. So here what we are doing. So initially it is in stage 0. We are applying Hadamard. After Hadamard, 50% it will generate 0, 50% it will generate 1. But once you do measurement, okay, the superposition state will get collapsed. Either it will get 0 or 1. So that is why superposition you cannot see over here. It is collapsed. Either it will pointing to 0, either it will pointing to 1. The probability is not changing because this software has some glitch. I think so. Otherwise, it will pointing to only 1. Software glitch. Any of you able to get only one value in your probability or showing for all? Okay, software glitch. Soon they will fix, I hope so. No issue. But this is the logic. So click this measurement gate, press delete button. Click this measurement gate, press delete button. Again, you can see superposition phenomena. Again, you can see superposition phenomena. So go and check your coding part. So here you can see Hadamard gate. H stands for Hadamard gate. So where we are locating in Q register Q0. Are you able to do? Go to view, go to panels, disable code editor, right? Then what you are doing? You delete this Hadamat gate. Okay. You place identity gate. So what it means? Before this, it is in stage 0. So we are placing an identity gate. It will do nothing. It is like a pause button. Pause button, or you can say it will retain its states. It will retain same state. So nothing will happen if you apply Hadamat identity gate. It is not like a barrier. It will stay in the same position. That's all. Suppose if you drag and drop NOT gate, you can see the state is changed into 1. I will retain the same state. So if you want to inspect, what you can do, you can enable this tool, inspect. So all of you enable this inspect tool. Inspect. So enable this inspect and you can play your circuit level by level. So click this. So from 0, it is pointing to 1. Click this. It will retain the next state, right? So we have only 2 states. So go back. Now play, right? So disable this. What we can do, we can place more gates. We can place more gates. Enable inspect. So now it is in stage 0, right? So play here. It will come to NOT. It will come to first NOT gate. That is why pointing to state 1. Press the next layer. It will come to Hadamat. You can see equal superposition at the same time, right? So click next. It will come to next NOT gate. Click again next. It will come to identity. So whatever happens Hadamat gate, the same state will be retained. So if you have multiple gates, you can inspect by enabling this tool. So delete all these gates. So we covered NOT gate, then we covered Hadamat gate, we covered identity gate. Next, what we do, we try to identify S gate or Z gate. So apply Z gate over here. And observe the output. So it is in stage 0. If you are applying Z gate, what will happen over here? What is the meaning of Z gate? Can anybody say? What is the meaning of Z gate? It will do phase flip. Whether you can see any phase flip over here? Exactly. If you are in stage 0, what happens? Z gate will not operate in stage 0. Okay. Anywhere in your Q sphere, it will enable a phase flip. A phase flip, and this flip is about pi values. Okay. So we cannot see any changes using stage 0. So what we do, we try to put a NOT gate over here and see the phase change. The phase change can be notified by this color. This color. All gates are unitary. All gates are unitary. Even NOT gate also unitary. So pi phase difference you can see over here. The red color it is pointing to pi. The blue color, navy blue, pointing to 0. Okay. The combination of this purple and blue is pointing to pi by 2. The combination of this orange and blue pointing to 3 pi by 2. So physically, you cannot see any changes using Z gate, but you can see the change in phase color. All of you able to see the difference? So please play through NOT gate Z. So delete one more Z. It will introduce one phase. Delete one more Z. It will retain its phase. The same thing you can do using your Y gate. So drag and drop Y gate. Are you able to see the difference? So Y gate will introduce pi by 2 phase difference exactly in top of this phase color. So it will do bit flip. So it will do bit flip from stage 0 to state 1 along with pi by 2 phase flip. So you can see the difference. In state vector, it is actually with angle. Okay. In terms of probability, in terms of measurement, no need to know about what is the phase angle. Only about the values. So until this is quantum. Okay. So if you do measurement, it becomes into classical. In classical, there is no point of mentioning your phase. We can reverse the classical states, no issue. 0 and 1 belongs to classical. Stage 0, stage 1 related to quantum. But here you have additional degree of freedom. This color, it means you have additional degree of computation. That is the basic idea in quantum. So all this phase angle, you have additional computational freedom. Next, what do we do? Drag and drop Hadamard gate. Okay. Then apply S gate. Are you able to see the change? Like Y gate, it will introduce pi by 2 phase difference in XY plane. So that is why you can see this color code difference. Same way you can drag and drop T gate, then you can see changes in your color. At P gate phase, again you can see changes in your color. So this will be very helpful if you are writing very complex algorithm, if you are changing any rotations in your qubit. So remembering this color will give you a fair idea what you are doing in your circuit, what is happening inside your circuit. So delete all these gates. delete all these gates. So what are the gates we covered? Adamat, NOT gate, identity gate, T gate, S gate, Z. Okay. Same way you can cover with T dagger opposite to T, S dagger. We already covered in previous session, right? So also you can cover P gate, phase gate. Okay. So RZ, RY, all these are rotational gates. All these are rotational gates. I can make a list. It is easy for us. Okay. So you can see the difference. What are all the gates which is disabled, which means it is not a single qubit gate. So RXX, RZZ, RCCX, RC3X. So these are multi-qubit gates. So in this way, you can identify whether it is single qubit gate or multi-qubit gate. So all these are single qubit. Now we're going to discover multi-qubit. To do multi-qubit, we need to increase number of qubits. So how to increase number of qubit? Click Q0, click plus button. Are you able to see the difference? Now we have 2 qubits. So 2 qubit means 4 possible combination. 4 possible combinations. What are all the 4 possible combination? 0, 0, 0, 1, 1, 0, 1, 1. Now circuit is empty. Now circuit is empty. Circuit is empty. Stage 0, stage 0. That is why it is pointing to north pole. So north pole contains stage 0, stage 0. So same way, it is pointing to 0, 0. The full amplitude for 0, 0. If you do measurement, you will get 0, 0 value in terms of classical. Now look at your gate collection. Swap gate is enabled. Control NOT is enabled. So all these gates are enabled. So previously it is not enabled, right? Now some gates are enabled. So for an example, CNOT and swap gate. So CNOT and swap gate are multi-qubit gate or 2 qubit gate. So drag and drop CNOT. Drag and drop CNOT. So this is a control qubit gate. So CNOT stands for controlled NOT gate. So it will act like a switch. It will act like a switch. So Q0 will act like control qubit. Okay. So Q1 will act like target. You are able to control your target by controlling switching your control qubit. So this is what it means. The other name for this is extended NOT gate. Extended NOT gate. So it is like a soldering. It is like a soldering. So we soldered in Q0 wire and we are extending that wire. We are giving power supply for this NOT gate. We are giving power supply for this NOT gate. So NOT gate is controllable from Q0. So Q0 can control your NOT gate. So this is the meaning. Okay. So initially it is in stage 0. This is also in stage 0. So stage 0 is, it means there is no power supply happening in this wire. So no power supply, it means this NOT gate is not activated. Not activated. It means whatever over here, it will retain. It will retain as it is. So no power supply. So stage 0 means stage 0. So this is the first case. This is the first case. So how to enable this Q0? How to enable the power supply? Drag and drop NOT gate over here. Now what happened? Stage 0, stage 0. Okay, we implemented one NOT gate. NOT gate means it will negotiate the state. Now it is in state 1. Power supply will happen. So power supply will happen across the wire. It will come down also because we solved it. Okay, this NOT gate is activated. This NOT gate is activated. Now we will get state 1. Here also the power supply will happen. State 1. Are you able to get the idea? Any doubts? Now we have 4 possible states 0, 0, 0, 1, 1, 0, 1, 1 and the full signal strength for 1, 1. Initially it is pointing to North Pole 0, 0. Now it is pointing to South Pole 1, 1. So likewise, slowly try to learn the gate. Okay, if you got confused, so click here, inspect. So click next. Now it is pointing to NOT gate. So the first gate is Q0 is state 1. The Q1 is stage 0. That is why pointing to 0, 1. So next, play the next layer. Control NOT gate will enable the same state in Q1 also. Next what I do, drag and drop control NOT, drag and drop control NOT. So right click this gate, right click any gate, click info. So this will give information about your gates. I'll note this point. Right click any gate to get information. Are you able to see the information about any gates? So you can see the phenomena, where it is used. You can see the Qiskit API reference and you can see the definition also. So this is the quick way to learn about any gate. So somebody asked how to modify the control and target. What do? Click this gate because it is classical, sir. Because it is classical. NOT gate is classical. Extended control NOT is also classical. What logic it will use? Only classical logic. Negotiation, right? Bit flip, state flip. So click edit operation. So click edit operation where you can see the control and target. If you select Q0 to Q1, automatically Q0 is changed as target. Are you able to do inverse? So click edit button to change between control and target. So click here, you can edit, you can see information, right? You can zoom it with a definition, right? You can cut, you can copy, like this you can do whatever you want. Suppose if you have multiple gates. Okay, we need to do the same process again and again. What you can do, you can select the entire gate. Okay, you can copy, you can paste. Are you able to get the point? And you are able to group it also. You are able to group it. You can give some name. So it is like a function, recursive function, recursive gate sequence if you want to write in your circuit. Yes, we can do Control Z. We can do Control Z. Check whether the gate is available. If it is not available, go here. Okay, so go to edit, add control. Now it is Control Z. Okay, so what you can do, you can select Z gate, go to edit, add control. Okay, same way you can do Control Y. Same way you can do Control Hadamat. Try this, you get to know. So when you can see changes in Z gate, only in state 0, not in state, only in state 1, not in state 0. So what do you do? Try to put over here. Now you can see some changes over here. Okay, great. So try to do Control Y. So drag and drop Y. So click here, add control. Now we can create Control Y, CY. So likewise, you can create control for all single qubit gates. Control for all single qubit gates. Now we are able to discover about swap gate. So this is swap gate. What this swap gate will do, it will swap information between two quantum bits. Now all quantum bits are in state 0. We cannot remove, we can hide it. That's all we can do. Because it is necessary for viewing, we cannot remove. No chance. You can do reset, that is possible. So you can do reset. You can hide it, but you cannot remove. Yes. So click this button. Click this button. It will hide. So go to view, go to panels, disable code editor. Okay, this is swap gate. What you can do, you can drag and drop a NOT gate over here. And you can see exchange of these states. Exchange of these states. Normally it is pointing to over here, stage 0. Okay, stage 0. Stage 0. Now we applied NOT gate. NOT gate means power supply will be there. State 1. And this is swapped over here. And I will change for 0. Imagine no power supply means blue. So it is swapped over here. So this is an example for swap gate. Now drag and drop NOT gate in Q1 and you can see exchange between your quantum states. Right? So try to explore all these gate one by one. All these gate one by one. Okay. Next, what we do? We try to implement a NOT gate. We try to implement a NOT gate. So state 0, state 0. Now it is converted into state 1. Here it is state 0. So that is why 0, 1. You have the combination of 0, 1. I will enable the state vector instead of probability. So drag and drop this NOT gate in Q1 and you will obtain 1, 0. So 0 for Q0, 1 for. We can save and we can export also. You can save your file. You can make a copy. Okay, you can make a copy. You can export. Because you cannot store your files over here. That is the problem, right? So check. Yeah, we can store, no issue. Qiskit. Qiskit. You can save your file, no issue. Then what you do? Drag two NOT gates. Now you are able to achieve 1, 1 state. So we explore 0, 0, 0, 1, 1, 0, 1, 1. Next, what we try to do? We try to implement a Hadamard gate in Q0 and see how it is explored. So what Hadamard gate will do? It will generate state 0 and also it will generate state 1. So that is why superposition is generated between only two states. Superposition for 0, 0 and 0, 1. It is not generated in Q1 because Q1 always generates state 0. Yes. What we can do? We can apply one more Hadamard gate. We can apply one more Hadamard gate. Now all superposition states are explored. Now superposition state is explored for all possible qubits 0, 0, 0, 1, 1, 0, 1, 1 at the same time. So this is one way to create superposition. The other way, what you can do, you can delete this Hadamard gate, right? And you can create control NOT. Now it is in superposition. Now it is in superposition, right? But it will create a special superposition state. Special superposition state, which is called entanglement state. Here superposition is controlled and it is created between only 0, 0 and 1, 1. Yes, sir. Any break is there? Hello. Am I audible, sir? Hello. Organizer, sir?
No. Sir, could you please take a break for 3 minutes?
No issue, sir. We can take.
Yeah.
Thank you. Thank you.